In this video, we'll talk about the column space of a matrix M, and I hope that you have watched the last video already about the row space of a matrix M. And the concepts of both videos look very similar, but when you try to find the column space in this video, it is actually slightly different from the last one. And let's look at the definition first. For any given matrix, now you have to view the matrix in terms of the array of numbers. They are listed in terms of columns. You see, like column 1, column 2, etc. And then the column space of M is basically just the span of all the column vector. You see? And let's look at an example now. Please look at the current case, which is a 2 by 2 matrix. And basically now you have a 2 column vector, right? So I can list the 2 vector as a column now. And for those of you who are good at the arithmetic, you can easily see that column 2 is actually 2 times column 1, right? And now, if you think of the column vector to be on the xy plane, this fact basically means that the two column vectors are staying along the same line, which has the direction dictated by one of the column vector. Let's say column one, the rational vector is like this. This is column 1, and column 2, because the length of the column 2 is extended by 2, but it is essentially on the same direction. It's like 2 times column 1, which is basically column 2. So what does it mean? It means that when you look at the span of the two column vectors now, basically now it's just a one-dimensional subspace in R2. Right, and we can describe this one-dimensional subspace by basically using this line, right? And let me write it down here. So basically, it's a straight line that passes through the origin, and the direction of this line obviously is governed by the direction of column 1 or column 2. And let me make a note here. So the note is that row operations you usually carry out when you solve a linear system actually change the column space of a matrix M. And for example, now let's look at the current small matrix 2 by 2, and of course you can notice that we can reduce the matrix by using row 2 minus 2 times row 1 for the update of the row 2. In that case, you're getting a 0 row for the second row, right? And let's call the new matrix to be M prime. And let's look at the column space of the two matrices here. You see, if you look at the two columns here, and now you can notice that for the second column, it is actually 3 times the first column, right? So this case is quite same as the first example we described. Basically, if you look at the column space, because the two columns have the same directions, basically it means it's a one-dimensional subspace passing the origin, and the direction of this line is governed by the column vector. For example, the column vector 1 is having the x-coordinate 1 and y-coordinate 2. So you're having a column 1 like this, and column 2 of course is much shorter. The length is 3 times the length of the column 1. So anyway, that's the span of the two columns here, and that's basically the column space of the matrix M. So basically, it's a one-dimensional subspace in R2, right? And let's look at the new matrix M prime after the row reductions. And you can look at the two columns now. The two columns are basically 1, 0, and the second column is basically 3, 0, right? And obviously, you can easily notice that the second column is 3 times the first column, right? And they have the same direction. And if you try to describe the column space, and basically, is essentially just the x-axis, because the x-axis is governed by the direction of these two vectors, right? It's like something like this for the first vector, and the second vector has the length 3 times the first vector, right? And you see, and obviously, two cases the two column spaces are not the same, right? And the thing that is the same is that the current column space for the matrix M prime is still a one-dimensional subspace in R2 still. But actually, the actual line, they are not the same, right? If you look at the actual line here, and obviously they are not the same line, although the dimension remains the same. There's another thing which remains the same, which is the relations among the columns. You can see for the first matrix, the second column is 3 times the first column, right? You can take a note now for the new matrix, the second column is also 3 times the first column. So these are the things that remain unchanged. So I make the second note here. So please look at my current note here. We have explained the last example already. The row operations actually change the column space of the matrix, but it doesn't change the dimension of the column space actually. So the second point is more important. It's about the fact that the dependency relations among the columns remain unchanged. Just like the last example, if the first matrix, the old one in M, there are certain dependency relations among the two columns, we expect the same dependency relations also appear in the new matrix after the row operations. And by using this fact, it can actually help us find the column space and describe it if the matrix M actually has a higher size. And let's look at the next example. So please look at the current matrix now. I would like you to describe the column space of this matrix. And now you can see there are actually 6 columns, right? Because the size of the matrix is actually 4 by 6. There are actually 6 columns. And now to describe the column space, which is not that easy. First, each column now has 4 coordinates, right? It means what? And it means that when you look at the column space, which is the span of all the columns, this space must actually sit in R4 because R4 also has 4 coordinates. Although we have 6 column vectors, it doesn't automatically mean we get the whole space R4. It doesn't mean that. The dimension can be 4 or less. Let me make a note here. So it can be at most 4, which means it can be something less like 2 or 3 or maybe even 1 dimensional subspace in R4. And to determine that, as we have noted in the last video, the row operation matters and it helps a lot. But in the current case of the column space, as we noted earlier, the fact is that after the row operations, the new matrix actually has its column space changed. But fortunately, we understand that although the column space is changed, first, the dimension of the column space is not changed. Second, the dependency relations among the columns is not changed. But anyway, let's carry out the row operation now. So you see, after certain row operations, you should be able to arrive at a new matrix. Let's call it M prime. And let's look at the column vectors now. If you try to check out the column vectors, let's call it C1 prime, C2 prime, etc. up to C6 prime. You see, it's quite obvious that the first 2 columns give us the same direction, right? So for example, it means what? It means when you try to determine the dimension of the column space, the second vector is redundant if you choose the first vector already. So I hope you get my point. And similarly, you can look at the third vector and the fourth vector. Both have non-zeros on the first 2 entries, right? And of course, these 2 vectors, um, they are not on the same direction as C1 and C2, right? They are not the same. So, and please look at the last 2 vectors, C5 prime and C6 prime. They have 3 non-zero entries in the first 3 coordinates. So I think basically it means what? For example, I can pick first row, the third row, and the fifth row. If you pick these 3 rows, basically it means that give us the column space of this M prime, right? Will generate the whole column space of M prime because of the fact that, for example, I've chosen C1 prime already, so C2 prime is redundant. We don't have to put it in the span when the 2 vectors have the same direction, so we just have to choose one of them. And among the vectors 3 and vector 4, we can choose one of them also. And also among 5 and 6, we can choose one of them only. So it means that's the way we get the column space. And if you recall the concept of basis, I'm looking at the basis actually. So let me put it here. The column space of M prime is actually spanned by the 3 vectors here. It means it's actually a 3-dimensional subspace in R4, right? And to describe this subspace in a more careful way, we can say that we can use the basis, which is the C1 prime, C3 prime, C5 prime. That's what I said. Just using these 3 bases elements, it actually spans the whole 3-dimensional subspace already. And there are actually other choices of bases. Can you see why? Because, for example, please recall the above. Among the first and the second vector, we can choose one of them, right? So, for example, instead of choosing the first vector, I can actually use the second vector, the third one, and the fifth one, right? Or there are other choices. For example, instead of using the third vector, I can choose the fourth one because they serve the similar purpose. There are actually many choices if you try to look at the basis of such a column space now. However, please go back to my current problem. My current problem is I would like to look at the column space of M, right? And I've told you already, after the row reductions, we get M prime, but we don't expect the two column space to be the same. But the only thing that's the same is about the dependency relations among the column vectors. It means what? It means if we go back to the original matrix M, I can just pick the three columns, the first, the third, and the fifth one, to be the basis of our current column space of M. And let's go back to our current space M. We can simply answer the problem in this way after understanding the M prime, but we couldn't just directly use the first, the third, and the fifth columns in M prime to generate the column space of M because as I told you, the space is already changed. Um, the thing that is not changed is about the dimension of the column space of the two matrices and also the basis. But I can simply use the same relations in the sense that I can just pick the first, the third, and the fifth vectors to generate the three-dimensional subspace. And of course, there are other choice of bases, same as how you arrive at them. For the M prime, I can simply use the second vector, the third one, and the fifth one, right? And there are also other choices. Or you can write it in a big way. The three basis vectors are basically the first vector, the third one, and the fifth one, right? And that's the final part of this video.